Hello, my name is Alex Hasikos, and in this video I'm going to be presenting a joint work with Emanuele Bellini, Philippe Gaborit, and Victor Mateu, named Enhancing Code-Based Zero-Knowledge Proofs Using the Rank Metric. Our paper is going to be presented on the 16th of December in 2020 at Cannes 2020. So in this talk, I'm going to be first presenting the contributions, explaining some preliminaries and some definitions and notations to understand the commitment scheme. Then I'm going to present the commitment scheme, give some performance metrics you have collected, and finally conclusions and future work. So in 2012, Jane et al. Published a work called Commitments and Efficient Zero-Knowledge Proofs from Learning Parity with Noise. So in this work, they have constructed a commitment scheme and some zero-knowledge protocols for proving the knowledge of valid opening, proving linear relations, and multiplicative relations. And in the main idea of our work is to port these constructions from the LPN problem, learning parity with noise, to the rank syndrome decoding problem. So we have designed, apart from the commitment scheme, which is perfectly binding and computationally hiding, we have also designed interactive protocols for knowledge of valid opening, proving linear relations, and multiplicative relations. In addition, we have computed parameters for both variants, the LPN variant and the RSD variant. Lastly, we have implemented and compared in terms of performance and efficiency both variants for 128 bits of security. Note that for the LPN variant, the authors, they haven't provided any parameters back then, neither any implementation that we could use. The highlights of this work is that we have constructed the first zero-knowledge protocol for arbitrary circuits whose security relies on the rank syndrome decoding problem. Our proposal is 60%, the proofs are 60% smaller than the LPN variant for the same security level. And the public parameters of our work are only 1% of the respective parameters for the LPN variant. So now let's see some preliminaries, notations, and definitions to understand these schemes. First, we're going to start with defining a linear code. So a linear code C is a vector subspace of fq to the n of dimension k, where k and n are positive integers such that k is smaller than n. Q is a prime power. For the rest of this talk and for interpreting our paper, we can assume that Q is 2. Fq is a finite field with Q elements. The elements of the vector space are called vectors or words, while the elements of the code are called code words. Two very important notions of code-based crypto is the generator and parity check matrices. So a matrix G with dimensions k times n is called a generator matrix of the code C if its rows form a basis. So when we have like a vector and we multiply it with the generator matrix, what we end up having is a code word belonging to the code. A matrix A of dimensions n minus k by n is called a parity check matrix of the code C if for any vector x, which is a code word, multiplied by the parity check matrix, we get 0. The Hamming weight of a vector v is simply the number of its non-zero bits, although in our work we don't use the Hamming weight, we use the rank weight. Just for completeness, we are also presenting the Hamming weight. And the rank weight of a vector is simply the rank of its matrix representations, i.e. the number of linearly dependent vectors. In this work, we have defined a function p, which I'm not going to be using for the rest of this video, but we thought it might be useful to explain it in this presentation for the people who are going to read the whole paper, and we assume that they're going to find it a bit tough to understand. So basically, this function p, given a matrix, a full rank matrix P and a full rank matrix Q, is basically a rank preserving transformation function. So the analogy for the Hamming weight is given a vector of a certain Hamming weight. Then if we apply transformations such as permutation over it, then we get the Hamming weight preserving function, and then we can invert it. The analogy with the rank metric is this function. So basically what we do here is that we get our vector and represented it in its matrix form, and we multiply it firstly by a full rank matrix Q of dimension n by m, and then by a matrix P of dimension n by n, and then we retransform it back to its vector form. And note that this function is invertible as long as P and Q are invertible matrices. Now let's move on to the decoding problem, which is the basis of both variants. So the decoding problem for random linear codes consists of searching for the closest code word to a given vector. So given the generator matrix G and a vector Y, which is computed by multiplying the secret X by the generator matrix and adding some error of a certain weight, find the pair X and E. The decoding problem is equivalent to the syndrome decoding problem, which is given H and S, which is equal H times Y, and the weight W of the error, find Y, where the Hamming weight of Y is W. So as it seems, the rank syndrome decoding problem, which we use in our construction, is the same as the syndrome decoding problem. However, the metric that is used for the weight of the error is the rank instead of the Hamming weight. So commitment schemes. Just give some very common definitions of what a commitment scheme is. So a triplet of algorithms set up, commit and verify is called a commitment scheme if it satisfies the following. On input L, security parameter, the setup algorithm outputs some public parameters. The commitment algorithm takes as input a message M from a message space and the public commitment parameters and outputs a commitment opening pair. And the verification algorithm takes the parameters, the message and the commitment, and an opening and outputs true or false. So commitment schemes have some properties, where in this case we have correctness, which means that the verifier should always return true if the inputs are honestly computed. Perfect binding, so with overwhelming probability for the choice of the public commitment parameters, no commitment can be opened in two different ways, which means that the prover cannot provide two different openings and still the verifier is able to verify both. And computational hiding means that the commitment is computationally hides the committed message if the commitments are computationally indistinguishable. So finally, let's see the commitment scheme. First of all, we have Q as a prime characteristic, M is the degree of the QR extension field, so we already said that Q is set to 2. The bit length mi of the message, M, and the bit length pi of the randomness, S. The length N of the linear code, and the rank rho of an error E. So the setup algorithm works as follows. We have the generator matrix GM, which is a full rank matrix of dimensions mi divided by m by n, and the matrix GS, which is again a full rank matrix of dimensions pi divided by m times n, and our commitment key is simply the concatenation of the transposition of those two matrices. To generate a commitment, given the message M, which we want to commit to, we have to generate a binary vector S of dimension pi, and then we have to sample an error vector E with elements in Q to the M, length N, such that the weight, the rank of this vector is rho. So to do that, we have to take the vector, convert it in its matrix representation form, and calculate the rank. And finally, the commitment is computed by concatenating this random vector S with M, multiply them by the generator matrix G, and then adding the error. And finally, we return C, the commitment, and the error vector S as our commitment. And now the verifier, given the generator matrix, our public key, our commitment, which is C, the message, and S, the randomness vector, we calculate E prime by adding C with the concatenation of S prime with M prime multiplied by G. And then if the rank of this vector E is rho, then we return true, otherwise false. In order to compare our scheme with the Hamming weight variant, we have to compute parameters for both. So apparently, for 128 bits of security, we have listed here the parameters. Something to note here is that the dimensions of the public key matrix for the rank variant are much smaller than the Hamming weight one, and this table corresponds to the Sigma protocol of knowledge of the valid opening, and the public parameters for this protocol for the rank weight are again much smaller in the rank weight. So the average communication cost is about 60% lower, while the public parameter size is 2 orders of magnitude lower. So the size of the secret in the zero knowledge proof is about 40% lower. So now let's talk a bit about the performance after we have implemented both variants. So our implementation was done in C++ using the NTL library from Victor Shoup for the arithmetic operations. And the benchmarks were conducted on a 2.9 GHz quad-core Intel Core i7 processor with 16 gigabytes of RAM. And we have also open sourced the source code of both variants, so you can access the code using this link. So this is the performance for the commitment scheme. And we have divided each step so that we can have a one-to-one comparison. Something to note here, the time it takes for the Hamming weight variant to compute a commitment is much lower than our work. And for the verification, it's sort of the same. And the reason for that is that the time it takes to generate a vector of a certain Hamming weight is much smaller than the time it takes to generate a vector of a certain rank weight. And you can see the time difference in the second column of the commitment. So taking just the metrics for the knowledge of valid opening sigma protocol, comparing the total times for the proof generation and proof verification, we can see that the rank variant is much faster than the Hamming variant. And the reason for that is a specific operation which essentially performs the Gaussian elimination to ensure that the vector is an image of a matrix. So because of the big dimensions of matrix A for the Hamming weight, in order to achieve a certain level of security, we see that this operation takes a significant amount of time to do. Whereas in the rank weight variant, the dimensions of matrix G are much smaller, so this operation is much faster. So for the proof of generation of the proof, is our work is a bit slower, but for the proof verification, the total time is significantly faster than the Hamming weight variant. Yeah, again, coming back to the formally noting the observations of the previous table. So the generation of the commitment is slower in the rank metric because the algorithm that generates an error of a certain rank is slower. The verification of the commitment is slower in the rank metric because computing the rank of a matrix is slower than computing the Hamming weight of the vector. The generation of matrix A in the Hamming metric is slower than G because of their difference in their dimensions. And the verification time of zero knowledge proofs in the rank metric is around 70 to 100 times faster than the Hamming metric. So essentially, this is the main breakthrough of using the rank metric variant in this case. So to conclude, we showed that quantum resistant commitments and zero knowledge proofs can be built upon the rank syndrome decoding problem. Our protocol is quasi-linear in the size of the circuit and has soundness of 2/3. We have provided implementations of both variants with parameters achieving 128 bits of security. And some future work that can be built on top of this work is, instead of using random linear codes, we can use structured codes, quasi-cyclic codes, to further improve efficiency and achieve even smaller parameters than the ones we have right now. We can investigate for a better proof construction than the iterative challenge response. So our zero knowledge proofs are sigma protocols that require multiple iterations in order to achieve all the properties. And we can also consider designing and implementing a 5-pass version. So yeah, that's it. Thanks for watching this video, and if you have any questions or recommendations, please get in touch. Thank you.